Today we are going to do chapter 6.1, but before I do that, I want you to show you the answer sheet because we're about to go to a new page on the answer sheet. So here's the answer sheet. We are in chapter 6, so I mostly just have to show you this part. Here's the first part of chapter 6. The other part is on the other side. Let's see. All right, that should be good enough. So next, let's the following page, the rest of chapter 6 and some certain other chapters. Okay, let's see. We have this. I forgot to put the pink stick out. I will do that after I'm done with this. Okay, a little bit closer on top, and then and a bit closer on the bottom. Okay, that should do it. All right, next, let's do chapter 6. The first page, which I have already scanned, but I just want to show it to you again. Let's see. Yeah, let it focus. And mostly this new page, of course. Okay, that should be good enough. So next, this is page 182 and 183. I don't have the bottom clamped. I forgot to clamp the bottom. I guess it's tolerable. Okay, like that. This part is a little bit bulged out. I better go clamp the bottom. Okay, now try again for page 182 and 183. Let's see, that is okay. All right, and then a little closer on top. And a little closer on the bottom. Okay. And finally, page 184 and 85. Let's see, we have this thing here. Okay. And then and a little bit closer on top. That looks different. Anyway, and a bit closer on the bottom. That should do it. All right, so let's start on chapter 6.1 on page 181. Now we have, first let's read about regions. Okay, now we have already discussed regions in chapter 1, but we are going to move on to change the definition somewhat to be more restrictive. So from now on, at least in this chapter, a domain is an open connected set. Okay, that is I think that's the same as before. That is, every point of D, the domain, is the center of some delta neighborhood such that all the entire delta neighborhood is contained inside D. And any 2 points in D can be connected by a broken line. The word broken line doesn't mean they're split apart. The broken just means they have a sharp corner that you can go, like this, but you still don't lift up your pen. So a broken line, and let's see, because the word line means straight line, so that's where this broken bit, somebody bent it, but it's not broken apart. So a broken line, where is it? Having a finite number of segments. So you can get from any point to the other point by making a finite number of turns and get to the other point. That would be an open domain. All the broken lines have to be contained inside D as well. If there's no way to get from one point to the other point with at least a broken line, then your domain got split up, and then that is not considered a domain in the current definition. A domain doesn't have to be bounded, but if it is, then it will call it bounded, and it's bounded if you can find some giant square that contains the entire domain. If no square can be found because the domain is going to infinity somewhere in one part of it, then it is not a bounded domain. Next, a region is a closed point set That is, now the region now is completely closed, okay, as we talk about region from this point on. It consists of a bounded domain, all right, and then plus its boundary points, and that means all the boundary points. And there will be, for example, if we have open circle, okay, plus the circle itself, then it would be a region. We shall assume further that the boundary consists of a finite number of closed curves. So if you look at the boundary, it has to be a finite number. It doesn't go nuts. It has an infinite number of closed curves. That would be weird. So the boundaries consist of a finite number of closed curves that do not cross themselves nor each other. Okay, and let's not even think about what that means. That is because right now we're just dealing with simple stuff, and that let's just keep things simple for now, okay? Because we're dealing with integrals right now, so then we don't need to get carried away about the region. Now, note that the regions here are special cases of what we studied in Chapter 1. We're not going to care about what we said in Chapter 1. That is, Chapter 1 we had a less strict definition of the region, but now we're going to have a more restrictive definition of the region. Now the region has to contain, the word region means something that's both the domain and its entire boundary. Now, normally, however, in our homework, the region will usually be given in terms of the boundary curves. Okay, that is, we'll define the region by telling us what is the boundary. For example, consider two concentric circumferences of some circle. So you have a circle, and they have the same center. Okay, so you have a donut-shaped thing, right, like this. And then, so these are two concentric circumferences, and the R will be the donut part, okay, minus the hole or the outside. So R will just be what's in here. Let's turn to the next page, page 182, plus the points on the circumferences. So so this will be the boundary, okay, and this will be the boundary. And this is one example. You might wonder, how can open domain have two closed boundaries? And this will be a quick example. See, this is one, and that's one, and they don't cross either, or something. Anyway, there is a region consists of a bounded domain plus its boundary points, and the boundary is a finite number of closed curves do not cross themselves nor each other. Yeah, okay, to cross means actually go past it, not just to reach. Okay, to reach is not crossing. To cross means you didn't just touch, but you actually went like this. That would be a cross. Well, anyway, let's move on. On page 182 on top, and we shall meet regions that we can also define regions by some kind of function, and like this. We have, let's phi of x and psi of x as psi of x, whatever. Phi of x and psi of x are continuous, okay, in the closed interval, and then one is strictly less than the other in the open interval of a to b. That is, one strictly less than each other, except for the endpoints. We don't care about endpoints because we're doing integration, okay? The endpoints don't matter in integration. So then the region Rx is bounded by the four curves, like something like this. We have this is A and B, and then there's that's the top one, and maybe that's the bottom one, and the bottom one is called phi of x, and the top one is called psi of x, something like that. You get the idea. So then this is called the region R of x. R of x means you have two straight edges in the x direction, and then the y direction you are allowed to have a graph. And so your region just have two straight sides. Now the region is then have the property that if x and y, x1, y1 is in this Rx, then the x1 will be between a and b, and y1 will be between phi and psi. Okay, and so that, and then a line that is vertical, you pick any vertical line, okay, will cut through the boundary of Rx in just 2 points. The reason for that is because phi and psi are functions, right? They have only one value. That's the meaning of the word function. So as an example then, let's consider R of -1 to 1, okay, and then minus square root of 1 minus x squared and plus square root of 1 minus x squared. That is definitely the unit circle. Now, and then in a similar way, or almost identical way, except changing x to y, we can define something called Ry, which is the same way, except that now the horizontal lines are straight, and then the boundaries are, the curvy lines are on the side. That will be Ry. And then now this region right here, as lying between two concentric circles, this thing is neither Rx nor Ry, because there is just no phi or psi you can come up with that can describe this. Okay, you need more than that. But it can be Rx or Ry if you cut it, right? You can just cut it. There are more than one way to cut it, but let's see. The book wants to cut it in this interesting way. It wants to cut it by vertical lines tangent to the inner circle. That is, the book wants to cut this region like this. Which is okay, but I can think of other ways to cut it. Either way, then we have 3 pieces, 4 pieces, 1, 2, 3, 4, and then and each one can be called an Rx or Ry or something, something like that. So that is that. And then if you cut it, then the vertical line from here to here will be the boundary of this guy and this guy, okay? They will have a shared boundary and will be, as a result, counted twice. And so each of these shared boundaries will be counted as the boundary of here and the boundary of there. So, yeah. And then, so next sentence, a region R is simply connected if its boundary consists of a single closed curve, which this one isn't, okay? Its boundary most definitely isn't consist of a single closed curve. It of necessity needs 2 closed curves to bound it. So the donut is, or whatever you want to call this thing, is not simply connected. It's not much of a donut because it's only 2D. And if a torus is a true donut. But I'll just call this thing a donut for now. And let's see. Next, the area Rx, and we have already learned how to calculate area from calculus 1. So we'll just assume the same information we knew from before for now. Okay, and then the diameter of a region is going to be its widest point, and that is the length of the longest segment that joins 2 points of R. So that would be the diameter. Being that the R is closed, you can always find 2 points that's the widest, assuming the region is bounded. Well, if it's not bounded, then of course the diameter is infinity. And the diameter doesn't have to be around a circle, okay? If you have a chunk that's long and narrow or something like that, the diameter is still the longest point in between, okay? And so that's that. Now, in the case of the circle, of course, the diameter is what it normally means, diameter. But any old object can have a diameter. It's just the longest point and longest distance in between. And then notice that by this definition of a diameter, a region, if the diameter of a region approaches 0, then the area has to approach 0 because the diameter is the longest side, okay? So as you squish it, as it gets smaller, it's the longest side is forced to be 0. Then the whole thing just collapses into a point. However, if you simply collapse it such that its area approaches 0, the diameter doesn't necessarily approach 0. As a case in point, imagine you take a sponge, okay, like that guy over there. Take a sponge and you just press it flat, okay, a sponge. is already somewhat flat. You press it flatter and flatter so that it becomes really flat. Then, but its diameter stays the same. It just got flatter is all. You press your sponge down, so it got flatter, but the diameter didn't change at all necessarily. So, just because the area goes to 0 doesn't mean the diameter has to go to 0. The diameter can stay constant, for that matter. So that's that. Next, let's consider section 1.2, the definitions. We are going to subdivide a region of area R, okay? And then and first let's look at definition 1. We have a subdivision of a region R is a set of closed curves that divides R into a bunch of little subdivisions, subregions Rk of area delta Sk, where and we have a finite number of them, okay? K goes from 1 to n. For example, in this picture that's in the book draws a very cute little thing over there. See that cute little thing, and it's very simple, right? It just let's see, can you see it? It seems very bright. Oh, I know. But anyway, so in this thing is divided into 12 subregions, right? And then in all but 2 of the subregions, it is composed partly of the boundary R. Okay, so they are only the regions are just little things, but most of them share the boundary. Now, the better way of making a subregion is just draw grids, right? Which is called equally spaced lines parallel to the axes. So we just draw these equally spaced parallel lines. That is a grid, a grid where everything is a square, and then we can decrease the distance between the grid so that you have a denser and denser grid to divide your region with. Now, if the distance between the line is small compared with the diameter of the region R, then most of the subregions will be squares. The smaller it gets, the more squares you get, and very few things that's along the region. Along the boundary of the region. So next, let's look at page 183, definition 2. The norm of delta, the norm of the triangle of a subregion delta. Did we call it delta before? No, we're just now calling it delta. Delta is the subdivision, just like before, okay? Except now our subdivision consists of areas, areas of things, or just subregions of things, rather than before we had little line segments. So now, but the idea is the same. It's just now we're dealing with 2 dimensions. Now the delta, the norm delta of a subdivision is the maximum diameter, as you can see, the maximum distance of your little square, diameter of the subregion produced by the subdivision. Okay? So if it's a square, then of course the diameter is the diagonal, the length of the diagonal. So let's look at definition 3, when we're going to define the so-called double integral. Okay, so we draw the integral sign 2 times over the region R, and that is of f x y ds is defined as the limit of the norm going to 0 of the sum of f psi k, eta k, that is some point in our little square that we drew, right, times the area of the sk. Now, and the sum point can be any point on there, okay, just pick a point. And then this limit, and as we force the grid to get smaller and smaller, and then add everything, there's more stuff to add up when the grid is smaller. And if this limit is approaches a clear limit, then we will call this the double integral. Now, okay. Now there are certain comments about double integral, like as you force everything smaller, then psi k and eta k has to move, right? Maybe you have to pick a different point as long as in the new sk that's getting smaller and smaller and stuff. And the same thing we've said before, so we'll just bear in mind of that. And we don't have to go and don't have to think too much about it. Let's move on to 1.3. Now, how do we know this limit exists? Now, we will give a sufficient condition for when it does exist. When does it exist? Theorem 1. If f of x, y is continuous in the closed region, Okay, now we don't call it interval, we call it region. Okay, so we have a region that is always closed. If it is continuous in this closed thing, then the integral, the double integral as defined in definition 3 will exist. We'll prove it later, okay, by the end of this chapter. So next, let's look at example A. We have a fairly simple region in example A. I'll draw it right here. It says x goes from 0 to 1, all right? Okay, x goes from 0 to 1, and then 0 to 1, and then it is defined by the two functions are minus x, this is minus x, and this is x. So we have a triangular region. And what are we doing? F of xy is just x. Okay, so f of xy only changes along the x line. It's the same, it's constant along the y, along this up and down, basically. All right, so then if that, in that case, f of xy is continuous, and therefore the limit 1 exists. And so we're going to choose subregions, and we're going to calculate this thing by the brute force, because we haven't defined how to calculate this limit yet. But in this case, being that it's fairly simple, right, we're going to do it a cute, interesting way, just for the fun of this. So what we're going to do is, our k is a square, of course, of psi delta x. And then what we have is, then what is the area then? Then the area is, let's say this is xk. All right, this come out as xk. That is, this distance here is xk. Okay, move it a little more over. This distance will be delta x. All right, and then we got up to xk minus k plus 1, right? And xk and xk minus 1 has a difference of delta x. All right, so we are going to calculate the f of xy is just x. So then the limit would be, according to this definition, we have we're going to calculate this thing as in x times, remember the area is defined as the x, f, in this case f psi eta is just x, and then times the area of sk, okay? So the area of this whole thing, we're going to add it as just a trapezoid. In other words, we're going to take the area would be, so what is the vertical? Being that this length here, down here is x, this is y equal to negative x and y equal to x. So this entire length should be 2xk, okay, right here. So this vertical length is 2xk, and similarly this is 2xk plus 1. And we're going to calculate the area of the trapezoid and multiply it by the function x, being that being the y value is the same. And so the entire integral would be the area of the trapezoid times the function x, which is let's see, I have it written right here. Okay, so the area is, if you think about this for a moment, then it'll make sense to you. But in any case, and so the area will be the xk, okay, that stands for f, the sum that we're talking about. So f psi eta is just, we'll pick xk, and being the f is just x, and times the area we're talking about is delta x, and that is the area of the trapezoid, which is the top times plus the bottom times the height divided by 2, right? So the top is 2x. Where's my formula? 2x, the top is 2x, k, the bottom is 2xk plus 1, I'm talking about the trapezoid here, times the height is delta x, and then divided by 2. And that equation will follow down, and next step, then it equals to, if you simplify a little bit, the delta x can factor out, because it is not affected in the summation of k, xk, and then the 2x and cancel out, so all we have in here, in the summation sign, is xk times xk plus xk plus 1, remembering the xk plus 1 is xk plus delta x, right? And then we plug that in, we end up having down here, okay? The rest of it, I did it the hard way, and then I realized we don't have to go through all that. We'll continue doing, so then xk plus 1 is just 2xk plus delta x, and we get this part, which breaks up into two limits. And the first one is the integral, okay, the definition of the Riemann integral. The second one has two delta x's in there, which the first part is the Riemann integral, and then which is finite times delta x. When delta x is going to 0, that is just 0, so we can ignore that. So this thing then equals to the integral, which integrates into 2/3, and that is what the book has here. Now please do this yourself as well, you know, if that sounds a bit weird. And if you think about it long enough, it'll all make sense. It's just a matter of getting, well, basically from this sentence to this sentence, okay, and calculating the trapezoid. And this only works because the function f is so simple, and also because these lines are minus x and x, so we can calculate the height of each trapezoid very quickly. So that's that. Just a cute little example to show you how we can do the double integral, the brute force way, okay? Without any formulas to help us. So we have to go back to doing limits of summation and stuff. So the fundamental way, so to speak. The direct way, let's say, we just calculated this one integral directly. Now, next, let's look at example B. Example B is a counterexample of what happens of a situation where the limit does not exist. And to do that, we're going to use the same idea as problem 5 from previous section, where we define the function to be 1 if it's irrational or something, and then 0 to be irrational or something like that. And so in this case, we have both x and y, so then we define it as 1 when x and y are both rational, and 0 when if that is not true. So then we have a clearly defined function that is not continuous, okay? And then so as a result, then when you do this, calculate the sum of function f over any region, then any small area will contain both rational and irrational numbers, which means you can choose f to be 1 or 0 in any kind of a subdivision, which means that you can force the limit to become 1 or 0. So then the limit will have to end up will have two values depending on how you choose f, which means the limit doesn't exist. And that's example B. So with that, we have finished this section, and let's look at the homework. So for homework on page 184, please do problems 1, 2, 3, 4, 6, and 7. Okay, and then now I'm not going to talk about the homework because they are very, very simple. Well, they might take a while, but actually I don't think they even take that long. So the homework is mostly is doing something similar to basic calculus, okay? So I will just show you what I did in the homework. So if you do get in trouble, maybe look at my stuff, see if it makes any sense. And but they're not worth talking about, really. They're just telling you to divide the region or something. If you look at it, you know what I mean. Okay, so that's problems 1, 2, and 3. So I'll just show you in my notes. See, the homework, this is it. This is all the homework there is, okay? And then that's problem 4, 6, and 7. And so that my answers are not necessarily the same as the back of the book. What I did is I just defined the functions as two broken lines instead of cutting it into more regions. And not two broken lines, two discontinuous lines. You know, they might have they're not C1, that is the phi and the psi. Well, if you look at it, you know what I mean. Okay, then they're not a big deal, I don't think. So that is the end of this section.